This is a dual signal PWM generator. The second signal is inverted and never overlaps with the first one. The entire circuit is made out of 3 stages. The first one is the oscillator. It will create the base frequency for the PWM signals. At the heart of this oscillator is an op-amp which we will use in a very simplistic way. I will first explain and build the individual parts, and when that is done, explain how they work together with the op-amp. We built the circuit on a so-called breadboard. On the back we can see how the pins are connected to each other. The long rows for power and the short ones for connecting components. This is a power supply for breadboards. It takes 12 volts from a barrel jack or 5 volts from a USB-C charger. It provides power and ground to the long rails on the board, 5 volts on the left and 3.3 volts on the right. We need 5 volts for the circuit, so let's test if the rails are powered. Regular multimeter probes don't fit in the breadboard holes. Those probes use banana plugs, so I take some banana plug to crocodile clip cables and put them into the multimeter. Those clips then grab jumper wires which do fit in the board. That's a free tip from me. Other free tip. Put the multimeter in DC voltage mode, not AC. 5 volts, perfect. Now we install the IC which contains the op-amp. There are actually 2 of them inside. Got a schematic on paper. Very useful when connecting it to the rest of the circuit. That notch on the top is also on the actual IC, so you know which way is up. So the IC has a VCC pin at the top right. Let's get 5 volts from the left power rail to that pin. If we cut the wire 3 points further than the hole it should go into, then it will be just long enough after stripping the coating. Now for the ground pin, that is on the bottom left. I know this looks like overdoing it, but I really want to make sure the power actually goes to the IC. The next part of the circuit is a resistor divider. I love those things, really. They are 2 equal resistors in series between 5 volts and ground. That results in voltage in between them is 2.5 volts. The resistors are of really high value, so little current goes through them, and that means that the midpoint voltage can be easily influenced, which is exactly what we will do. The op-amp can output a signal either 5 volts or ground. This voltage is sent to the same midpoint voltage, but through a resistor smaller in value, so it has a big influence on the final midpoint voltage. That will be either close to 5 volts or close to ground, but not all the way. And that last bit is important. First we do the 2 1 mega ohm resistors. I also like to test every component before placing them on the board, to make sure they work and that the value is correct. These component testers are really inexpensive from China. I have the circuit schematic and the IC schematic next to me. And we just saw how the breadboard is wired underneath. That, and taking your time, it is not that difficult to get components where they should go. More testing. I want to see the midpoint voltage at 2.5 volts. Great, that works. Now for the final resistor that connects the 2.5 volts to the first op-amp's output. Quick note, that final voltage is also fed into the positive input of the op-amp, just as the final voltage of this next small circuit will be fed to the negative input of the op-amp. The op-amp's output will also be fed through another resistor. And as this output is either 5 volts or ground, it will either charge or discharge this capacitor here. The voltage that the capacitor is at will be shared with the negative input of the op-amp. More testing, this time the capacitor, and I will now stop showing you that, as I suspect you get the point. Now placing the resistor, but I also need a connection to the negative input. So I decide to remove the resistor and do that wire first and then reinsert the resistor. Time to hook up my oscilloscope and see the signal. First, the signal at the capacitor charging and discharging. It should look more like some sort of triangle, but this is also good, I guess. And now the modified op-amp's output. That midpoint voltage with 3 resistors, I mean. Yikes, that should look more like a square wave signal. Guess we'll have to fix that. But first, let's look at how this circuit actually works. The output of the op-amp goes high when the positive input voltage is greater than the negative input, and goes low when the positive input is lower than the negative one. Let's start with the high output and see what that does to the circuit. The resistor divider voltage that goes to the positive input is close to 5 volts, but not all the way. It also is charging the capacitor like this. And that will actually reach the 5 volts and overtakes that other voltage. Now, the negative input voltage is actually greater than the positive one, and so the op-amp switches its output to ground. The resistor divider circuit now goes the other way. Voltage close to ground, but again, not all the way. So the discharging capacitor can overtake that and the op-amp output will switch high again. And so, that high-low sequence continues, making it an oscillator. Very cool, huh? I suspect the 1 kilo ohm resistor connected to the capacitor taxing the op-amp too much with too much current draw, deforming the square wave signal. Let's change that to a 10 kilo ohm resistor. That looks more square to me. Also, the charging curve looks more like a triangle. Big improvement. Now we have a nice triangle signal. We can use that in the next circuit. The main component for the second circuit is also an op-amp. This time we will be using a potentiometer. It will let us choose any voltage between the voltage attached to it and ground. Internally, it is a variable resistor divider with a total resistance of 10 kilo ohms. That, together with the op-amp, will allow us to change the duty cycle of the PWM signal. We connect that output voltage to the positive input of the op-amp. To the negative input, we connect the triangle signal that the previous circuit created. And then, done. The op-amp now outputs a variable PWM signal. First, the potentiometer. It has 3 wires and I do not know which one is what. I try to find the 2 wires that have a fixed resistance no matter the position of the knob. These will be the VCC and ground wires. The order does not matter. The third one will be the one outputting the variable voltage. So I give it 5 volts and ground and then measure the output voltage of the third wire. Did you spot the problem? I forgot to power the circuit. That's better. We have a variable voltage. That output voltage now goes to the positive input of the second op-amp in the IC. It is on the right side. Remember that schematic of the IC? Now we need to transport the output signal of the first circuit on the left to the negative input of the second op-amp. At this point, again, I am just following the schematics and remembering the connector strips at the back of the breadboard. So there is no thinking involved here. Time to hook up the oscilloscope again and have a look at the new output signal. That looks great. When turning the knob of the potentiometer, we can see the duty cycle change. And at both 0% and 100% duty cycle, the signal flatlines, either to 5 volts or ground. Now, how does all that work? Or better, why? Well, first we have the triangle signal, and then there is that variable voltage from the potentiometer. As long as the positive input of the op-amp, the 3 volts, is greater than the voltage of the triangle signal, the output of the op-amp is high, like this. But then they cross, and the op-amp's output goes low, like this, until they cross again. Now, what if the 3 volt signal from the potentiometer was lower, like 2 volts? In that case, the first crossover will happen sooner, and the second later, making the output signal low for longer. This is the third and final circuit, the signal inverter, also non-overlapping, like I said in the intro. I am starting to see a pattern here. More op-amps. And another resistor divider. This one is fancy. 3 resistors in series even. The midpoints are connected to each their own op-amp, but not to the same input. Very important. This has to do with a sequence of events that have to happen. The other inputs of the op-amps are connected to the same, now variable PWM signal. And the final PWM output signals. To understand why this works, we need to know 2 things. First, the input signal is a square wave, but zoom in close enough and the signal does not go from 5 volts to 0 volts or back in an instant. It takes some time. Second, when the inputs of the op-amp flip, meaning the other one is now bigger than the other, the output of the op-amp also flips, from high to low or back. So, the PWM signal dropping from 5 volts to 0 volts first passes 3.3 volts on the first op-amp, and then the 1.6 volts on the second. And because the second one has the input switched, first signal 1 goes down, only after that signal 2 goes up. No overlap. Same goes the other way around. Pretty clever, right? Here is the second IC with the other 2 op-amps we need. And some power. And the 3 resistors. Then feed the output of the previous circuit to the 2 inputs of both op-amps. Now I need to trim the legs of the resistor. Let's get this oscilloscope to work and look at both outputs together.